Use a finite approximation to estimate the area under the curve f of x is equal to 16 minus x squared and above the x-axis between x's negative 4 and x's positive 4, using first a lower sum with 4 rectangles of equal width, and then using an upper sum with 4 rectangles of equal width. So while we have two different cases here, the setup for both cases is the same. So let's begin there. So again, we are given here, we have the curve f of x is equal to 16 minus x squared, and this is such that x is greater than or equal to negative 4, less than or equal to positive 4. So thinking back to our strategy, the first thing that we need to do is define the number of rectangles that we're using. So in both part A and part B here, we're using 4 rectangles. So we'll let n be equal to 4 rectangles total. And we'll also let our interval here A to be, our x naught to x sub n, be this closed interval negative 4 to positive 4. So the next thing that we need to do is find the width of each one of these rectangles. And we recall that the width, delta x, is equal to the length of your interval, so x sub n minus x naught, all over the number of rectangles. So I have 4 minus a minus 4, all divided by 4. So we have in the numerator, we have 8, all divided by 4, which leaves us with 2. So therefore, the width of each one of our rectangles here will be 2 units long. The next thing that we need to do is subdivide the interval using our width. So we want to subdivide the interval. So this is a great way to check your work. So keep in mind that our full interval here that we're trying to divide is negative 4 to positive 4. And let's give ourselves a little more room. So we start with our first endpoint here. So we can say, actually, we'll say negative 4 to positive 4. We want to break this down into 4 subintervals or 4 rectangles. So we start with the endpoint negative 4, and we're going to think to ourselves, all right, we have negative 4 plus a width of 2. So negative 4 plus 2 leaves us with minus 2. So there's your first subinterval. The next interval starts at the previous endpoint, so we have negative 2. And again, we think to ourselves, all right, negative 2 plus 2 gives us 0. So there's our second subinterval. So the third subinterval starts again at that same endpoint, so we have 0. And we think to ourselves, okay, 0 plus 2 is 2. There's our third subinterval. And then last but not least, again, starting with 2, we think to ourselves, 2 plus 2 is 4. And hey, that's the end point of our given interval. So it's a great way to check to make sure that you have the correct width and that you're using the number of rectangles properly. You should always end up, the first interval should start at the first endpoint and the last interval should end at the last endpoint. So these are the subintervals that we're going to use here. All right, so now we're ready to go ahead and sketch ourselves a picture. So we want to sketch the graph, and then we'll draw a rectangle within each of these subintervals. So here we go. We have our y-axis and the x-axis. And then so thinking about our subintervals here, we'll just do a 2 by 2 scale on x. So there's negative 2, here's negative 4, and then we have positive 2 and positive 4. If you have graphing paper, I encourage you to use it. And then, so here what we want to do next is we got to find the corresponding y values. So let's actually drop down below and think about that. So when we're calculating these heights, or the corresponding y values, you always want to use the endpoints of your intervals. So we're going to need the y value for when x is negative 4. We're going to need the y value for when x is negative 2. We need the y value for when x is 0. We need the y value for when x is positive 2. And then we need the y value for when x is positive 4. And then based off of these numerical values, we'll establish our y scale. So plugging in, again, the function you're using is your given function. F of x is is 16 minus x squared. So when x is negative 4, we have 16 minus 16, which gives us 0. When x is negative 2, we have 16 minus 4, which is 12. When x is 0, we have 16 minus 0, which gives us 16. When x is 2, we have 16 minus 4, which is again 12. And last but not least, we have 16 minus 16, which gives us 0. So now we have all of these y values, which we can see are all divisible by 4. So let's use a 4 by 4 scale on y. So say 4, 8, 12, and we'll say there is 16. So let's sketch this graph using the endpoints we just calculated. So we have negative 4, 0. We have a point at negative 2, 12, a point at 0, 16, and then another point at 2, 12, and then 4, 0. And so here is our bounded region. If we connect those endpoints with a smooth curve, we can see the region that we want to approximate the area for. So we are trying to approximate the area under this curve, but above the x-axis. So now what we need to do is divide this into rectangles, or we want to draw a rectangle over each of the subintervals. So we have a rectangle from negative 4 to negative 2. So here is our first rectangle. We have another rectangle from negative 2 to 0. So here is our second rectangle. Our third rectangle is from 0 to 2. Here's that third one. And then last but not least, we have a rectangle from 2 to 4. So you can see here, looking at these rectangles over this region, that we're going to get either an approximate area that's too big or too small. So the number of rectangles you use is important. The more rectangles you use, the more accurate your area approximation will be. Okie dokie, so we have everything that we need. We have all the y values, which will produce the heights. Let's keep in mind, we know that our width of each one of these subintervals, or these rectangles, was 2 units long. And we can now go ahead and approximate with a lower sum and then an upper sum. So in part A, we want to approximate the area with a lower sum. Now, when we say we want to approximate the area with a lower sum, this means that we want to use the minimum y value in each subinterval. So we want to use the minimum y value in each subinterval. So if we look up at our graph, the lowest endpoint in the interval negative 4 to negative 2 is going to be negative 4. In the interval from negative 2 to 0, the lower endpoint, or the minimum endpoint, will occur at negative 2. When we think about the interval from 0 to positive 2, we want to use the endpoint at 2. And then last but not least, when we're in the interval 2 to 4, we're using the endpoint at 4. So we can see here, when we're finding or identifying those heights. So again, repeating this, in the interval negative 4 to negative 2, we're using a height of negative 4. In the interval from negative 2 to 0, we're going to use a height occurring at negative 2. When we're in the interval from 0 to positive 2, we are using the height at the endpoint for positive 2. And then last but not least, when we're in the interval from 2 to 4, we're going to use the endpoint at 4 because it produces the minimum value with a smaller value. So this is going to be 0, 12, 12, and 0. So we'll take these heights and we'll approximate the area. So we can say that the area is approximately equal to the width multiplied by the sum of the heights. And I'll say the sum of those f of x sub k, the sum of those heights. So this will be approximately equal to a width of 2 multiplied by the sum of our heights here, 0 plus 12 plus 12 plus 0. And so that's approximately equal to 2 times 24. So the area using a lower sum is approximately equal to 48 square units. And so this is our final answer here for part A. And now let's go ahead and we'll think about how this is going to change when we use an upper sum. So I want to make sure we can still see our graph while we do this approximation. All right, so part B, you want to approximate the area with an upper sum. So if we're approximating the area with an upper sum, what endpoint do you think you'll use? You are correct. We're going to use the maximum y value this time. So you want to use the maximum or the largest y value. The maximum or the largest y value in each interval. So again, if we reference back up here to our graph, in the interval, we're thinking about the interval from -4 to -2. I want to think which y or which x value we're going to use. Which one will produce the larger y value? So this time we're going to use the endpoint -2 because that's going to produce the larger y value. When we transition to the interval -2 to 0, again, looking at the graph, we think which one of those endpoints produces the larger y value? And 0 does. So we have y is equal to f of 0. So now thinking about the interval from 0 to 2, again, which x value produces the larger y? And again, it's still at 0. So we have f of 0. And then last but not least, we have the interval from 2 to 4. And we think which one of those endpoints produces the larger y? And it's 2. All right, so we know that f of -2 is 12, f of 0 is 16, f of 0 is again 16, and then f of +2 is 12. So again, these are the heights for the upper sum. Okay, so we can approximate the area. So again, we know that the area will be approximately equal to the width multiplied by the sum of the heights. So this is approximately equal to the width we know is 2. And now we're going to take the sum of each one of these heights we just determined. So we have 12 plus 16 plus 16 plus 12, which is approximately equal to 2. So we have 12 plus 12 is 24, plus 32 gives us 56. So we have 2 times, not 52, 56, minus 1 on my test. So we have that the area is approximately equal to 2 times 56 is 112 square units. And so this is our final answer here for the upper sum. So we can see here, looking at our upper sum and the lower sum, those are two pretty different numbers here. Right? So one is giving us a gross overestimate, while the other one is giving us a gross underestimate. So again, the more rectangles you use, the more accurate your area approximation will be. And then in the next section, we're going to look at a technique where we can take the limit. We can think about, what if we used infinitely many rectangles? And then we can take the limit as n is approaching infinity to get that exact value. So something to get excited about.